What does infinity mean? Is it a very large number? Well, infinity is not a number. Infinity is a concept that something is unlimited, endless, or it has no boundary. Let me explain. Suppose we are asked how many numbers are there between 1 and 2. Then, obviously, 1.1 is a number between 1 and 2. Likewise, 1.11, 1.111, and so on. I can keep on adding 1 behind and get another unique number between 1 and 2. So, how many numbers we have between 1 and 2? And the answer is infinity. Now let's talk about another concept related to infinity. It is infinitesimal. Infinitesimal is 1 over infinity. So what's the value of 1 over infinity? Let's take an example. Suppose I have a pizza. I cut it into 2 equal pieces. Now I have 1 half. Then I can cut it into 1/4. 1 over 8, 1 over 16, 1 over 32, 1 over 64, 1 over 128, and so on. At this point, I barely have a pizza. What happens if I cut it into infinite pieces? Which of course I can't, but will it be 0? Since infinity is not a number, 1 over infinity is also not a number. Its value is somewhere near to 0, but not equal to 0. These concepts are the foundations for understanding calculus. Now let's look at some graphs. Let's consider a function y equals to 2x plus 3. Now we increase the value of x by only 0.1. Then the graph is shifted by only 0.2 units upward. But if we increase the value of x by infinitesimal, the change in y would be so small that it is better to consider the graph did not change at all. Now let's talk about a new concept, limits. Limits describe how a function behaves near a point instead of that exact point. Let's look at an example. Consider a function y equals to x plus 2 with a point 1, 3 in it. If we gradually increase the value of x till it becomes x equals 3, the value of y gets really close to 5. This is called left-hand limit. Similarly, at point 5, 7, if we decrease the value of x till it becomes x equals 3, again the y value approaches 5. This is called right-hand limit. So the limit is 5. Now let's look at another example. In this function y equals to x plus 2, look at the point x equals to 3. The y value is missing at this point, which is indicated by a hole. So the functional value at this point does not exist, but the limiting value does. And the limiting value is again 5 here. A question for you. Find the functional and the limiting value of the function f at x equals 6. The answer is, the limiting value is -3, but the functional value is -5. Now there's a better definition of limit, and the definition is F7 delta definition. Let's see what it says. Consider a function y equals f of x. Points a minus delta, and a plus delta lie on x-axis. Similarly, points L minus epsilon, and L plus epsilon lie on y-axis, where epsilon and delta are positive numbers. Suppose the limit of the function at a is L. Now, if you pick any value of x that lies within the range of a minus delta to a plus delta, then the definition says that the distance between f of x and L is less than the epsilon. So all of this saying is that if the limit L truly exists and we have a positive number epsilon and delta, and we take any value of x that lies within the delta of a, then f of x also lies within the epsilon of L. Means our f of x will sit somewhere over here